Everyone, welcome to this second to last session of the OCaml at ICFP this year. We're going to start in a moment with my esteemed colleague Vesa Karvonen, who's going to talk about the new POSIX.
Thank you. So in 2015, Bob Nystrom published this blog post titled "What color is your function?" And there was this idea that if you have a language with blue and red functions, and you have this problem that if you want to try to call a red function from blue function, then it's going to be a problem. And it's a problem because those red functions are asynchronous functions, and well, you just can't call an asynchronous function from a synchronous function and obtain the result synchronously. So of course, the developers of OCaml24 knew how to solve this problem. Let's just introduce effects. And how did it turn out? Well, now we have all of these schedulers and more. I think we'll probably hear about 2 more today, who knows. And well, they are all mutually incompatible. So they all use different effects. And this means that, for instance, you cannot call EIO's IO APIs from a domain slip fiber, for example. And that's because a domain slip effect handler does not handle the EIO effects. So now we have functions of 8 different colors and counting. So it doesn't look good so far. So how do we solve this? Or what are the actual problems that we get from this is that now we're not just duplicating the effort to implement these schedulers. We have all other things, like we want to have libraries like HTTP libraries that need to do something asynchronous. And we have a massive amount of duplication of functionality. These libraries have to be ported to all of the schedulers. And this makes it really expensive to innovate. So if you want to have a new library for concurrency, you have an idea of how to do concurrency better, then you're probably not going to have the resources to port all of the asynchronous libraries to your scheduler, basically. And naturally, no one else does have that kind of time either, so they're going to have to pick and choose, like, okay, I have this library, I want to support this scheduler, but I don't have time to support all of those schedulers. So it's naturally going to lead to a kind of community split, or even now that we have like 10 different schedulers probably, then it's going to be like 10 different competing subsections of the community. And that's not really good. So how do we solve this? And the solution that we're proposing here is that we introduce an interface between schedulers and concurrent abstractions. So the idea is that this Picos interface, it's kind of like the POSIX of effects-based schedulers. So you program against the interface, and what you get as a result is kind of this picture. So in the center, we have the Picos interface, and then we have all sorts of concurrent abstractions, parallel algorithms, synchronization primitives, structuring models, and so on. And they all only depend on the interface. And on the other hand, the schedulers also depend on the interface, but they implement the interface. So they implement the scheduling part of the system. And because none of these things depend directly on each other, they only depend on the interface, then they naturally will work together. So all of these are basically like interchangeable parts of the system. You can run your code on different schedulers. You can use different structuring models in the same program, and so on. And then the question is like, what is the scheduler? And actually, we had in a previous session we had a talk about abstract data types or modules. But here's an example. Like we have a dispenser abstraction, so you can push things into a dispenser, and you can also pop things out of a dispenser. So this could be like a stack or a queue or a bag. And the thing is that this sort of trivializes the data structure. And what I mean by this is that if you have additional operations on a special dispenser data structure, like an operation that can pop multiple elements at a single operation, then if your clients using the data structure only use the dispenser interface, that they're not going to use this extra operation. So basically, we kind of have the same thing with schedulers. So what is a scheduler? If you look at the existing schedulers, then they basically have everything in them. They have the multiplexer, they have their own synchronization and communication primitives, they have probably their own asynchronous I/O integration, they have actors potentially, maybe they have structured concurrency, maybe they have a capability system, and so on. So what will happen with the Picos interface is that it only sort of gives you an interface to the multiplexer and timeouts. And that's basically what I think is just enough to implement everything else as libraries when you do it properly. And this will, in turn, trivialize the scheduler. So it moves functionally outside of the scheduler, which also means that if you have a custom scheduler, then you might implement certain things sort of inside the effect handlers. But the Picos interface actually requires certain things from the scheduler to be sort of unconstrained and to implement those constraints outside of the scheduler. That's the idea. Here's a kind of a motivating problem. What do we need to actually have in the interface to support these kinds of things? So there's like a snippet of code there, which doesn't really make sense, but the idea there is that it will basically block. So it protects a condition weight with a mutex. And imagine now that we would need to cancel this code. It's running in a fiber, and maybe we have an error in the program. We want to shut down the program, and we have to make sure that all the fibers will terminate. So there's a kind of a liveness issue there. So when we cancel this, we really want it to sort of terminate, so it has to unwind everything. But there's also a safety issue, like if the fiber happens to be in the condition weight, and then we cancel it, then it has to reacquire the mutex, because the protect function will unlock the mutex at the end of the scope. So we need to be able to address these things. Here's another example using kind of structured concurrency thing. So the idea is that we have a program that allocates some resources, and then we have this protected block where we have some sort of finalizer. It deallocates or frees the resources. But we also use fibers there. So we create a scope for fibers, and then we create or fork new fibers, which probably use those resources or may use those resources. And then what happens if this gets canceled? So what we need to make sure that actually when we execute the finalizer, then all of the fibers that might be using the resources, they have to be terminated properly. So the join after function there, it really has to wait for all of the fibers to terminate properly before it allows to return. And then the finalizer will run as normally. So these are the kind of motivating problems that I had. And now we're ready to go to the actual architecture of the interface. So it's basically based on a trio of abstractions which work together. And first of all, there's a trigger abstraction, which allows you to basically await for a signal from some other fiber or thread or domain or whatever. And then there's a computation abstraction, which basically allows you to sort of both observe and sometimes control an asynchronous computation. So it basically has a state, either it's running or it has been completed. And then there's the fiber abstraction, which gives an identity to independent threads of control, and also allows those fibers to control certain aspects of how the scheduler should work with them. And in a bit more detail, here's like an extract from the trigger signature. So we can see that it's a simple monotype. We can create triggers, and the idea is that you can then insert that trigger into some concurrent data structure, and then some other fiber or whatever can find the trigger from there and signal it. And we can also, as the owner, we can await on the trigger. And the idea there is that if the trigger has been signaled, then that will just return immediately. Otherwise, the scheduler will suspend the fiber. And eventually it will return either with none, which means that the trigger was signaled normally and the fiber has not been canceled. But otherwise, it might return with an exception and a backtrace, meaning that the fiber was actually canceled. And regardless of which outcome you get, you have to clean up after yourself. So if you inserted triggers or modified data structures, then you have to make sure that you clean up everything afterwards. The computation abstraction, on the other hand, it does carry a value. And you can create it. It will be sort of empty in a running state. And it's possible to return a value to it, which turns the computation into completed computation. But you can also cancel it with an exception. And it's also possible to check like whether the computation has been canceled or not, but also to await for the computation to finish, and it will either return the value that was returned to the computation, or it will raise an exception. And what's more interesting, though, is that it's possible to attach triggers to computations. So that allows anyone to observe the state change from running to completed of a computation. And then there's also the operation for timeouts, which we'll not get into in more detail here. A fiber, the fiber module provides some important operations, like the ability to yield. This just asks the scheduler to reschedule the current fiber. But more interestingly, we have the fiber type, which again doesn't carry a value. We can ask for the current fiber. So if you're running code somewhere and you want to figure out what's the current fiber, you can ask it from the scheduler. But you can also create new fibers and spawn them on the scheduler. And the fiber, interestingly, has a couple of pieces of state. It has a computation. So every fiber has a computation associated with it, which can be manipulated to set up scopes for cancellation. And you can also manipulate a Boolean flag, which tells whether the scheduler should propagate cancellation to the fiber when it performs effects. And there's also fiber local storage for extensions, which we are also not discussing today. So the cancellation protocol is fairly simple. So the idea is that every fiber is always associated with a computation. And when you await for a trigger to be signaled, the scheduler attaches the trigger to the computation associated with the fiber. So what that means is that if the computation is completed, canceled, or returns, then the trigger will be signaled. And that allows the await to unblock, and the fiber will basically then terminate. And all of this is implemented partially, so it's like an abstract class, and the way the missing things are implemented is through effects. So we have these 5 effects: await, cancel after, current, yield, and spawn, and these are to be implemented by the scheduler. And one of the contracts here is that the interface does not dictate which fiber to run next. So after any effect, the scheduler can decide which ready fiber to run next. And that's basically all. So of course there are contracts between the interface and the different parties, and there are also like additional operations which help. But basically, because it's all about cancellation, so about setting up contexts where you're expecting cancellation, and also reacting to cancellation. So what can you actually implement with this interface? And we have actually implemented quite a few examples. We have, with the Picos repository, we have 4 different schedulers. We have a single-threaded scheduler, multi-threaded scheduler, and then there's a randomized scheduler, which actually, after every effect, it randomly picks one fiber to run. There's also an interface to LWT, which doesn't really implement its own scheduler. It just runs everything on LWT directly. And there's also a scheduler called Moonpool, which has been ported to use Picos by Simon Kruanes, also known as C-Cube. We also have a synchronization and communication library, which has a standard library style, mutexes and condition variables, semaphores, a lazy module, an event module, and a few other things. And there's also a library for resource management, which interestingly has this ability to move resources from one fiber to another and do it safely so that there's no leak. And there's also a sample library for structured concurrency. There's also an I/O library using only the Unix module that comes with the compiler distribution. And there's also a simple minimalistic implementation of this co-HTTP library for Picos. And there's also an experimental tiny HTTPD daemon also by C-Cube. And yeah, so basically you could already write some applications with these. So here's actually a kind of toy program, not very interesting. We go through it very quickly. So it just basically forks 4 fibers. And here it actually uses the standard library version of Unix Sleep, which basically blocks the whole thread. So the scheduler cannot do anything while the thread is sleeping. And then it obtains the domain index, and then it prints the domain index, basically. So the mutex is here used mostly as an example. So yes, there's a mutex. And also it helps to make sure that the output isn't garbled. So we can then run this program on pretty much all of the schedulers. So we could run it on the single-threaded FIFO scheduler. So we can see that it runs all the fibers on the same default domain, basically. And then we could run it on the multi-domain FIFO scheduler, which actually runs all of the fibers on different domains in this case. Then there's the randomized scheduler. Again, uses multiple domains. And then there's also the LWT scheduler. So we can actually run this program already on multiple schedulers. So we have sort of validated that we actually have the situation that we saw in the dependency picture, basically. So it should be clear now that Picos is not a scheduler. It's at least much more than that. Here's another example. So we start with a couple of libraries. And then there's not very interesting stuff here, but this is basically like a client that posts a name to the server, and then the server responds with a body that says that hello something. And more interesting is the setup. We create this socket for the server, and we use the resource management library there so that we make sure that the socket will be closed eventually. We set up the socket. We make it non-blocking because that's much faster, basically. And we create this scope for fibers, which we terminate on return so that we can sort of automatically clean up things or terminate things. We create this fiber for the server. And then we create another scope for fibers where we run the clients in separate fibers, basically. Or we actually run, I must have forgotten, actually, there should be a fork there. But yeah, it basically runs the client code multiple times. And then we can, of course, run it with different schedulers. So here's just an example using the randomized scheduler. So we can see that it already handles the responses from multiple, using multiple domains, basically, running things in parallel. So yeah, what's missing is that this is just a sample. We could just as well be using libraries written by someone else if they just use the Picos interface, and we could use the same schedulers or different schedulers and so on. So everything is interchangeable and interoperable. So the interesting question then is, what about performance? And I should note that, I mean, Picos by itself, it's designed to be unopinionated. So it doesn't require you to use structured concurrency, for instance. And it has support for this parallelism safe cancellation, which is not supported by all the schedulers. It doesn't require I/O to be done in the scheduler loop. Some of the schedulers do that currently. And well, I have paid a lot of attention to performance. So first of all, here's a data point on memory use. So as an example, EIO currently uses about 504 bytes per fiber. With similar features, Picos takes between 160 and 312 bytes, so quite a lot smaller. And basically the 160 bytes is probably closer to what is the most common use case. And, also, this would actually be a little bit smaller because I think that the standard library allocates an extra closure, which wouldn't really be needed. And so we could get rid of that, and it would reduce that to 128 bytes per fiber. Also, I ported a few benchmarks. It's a bit difficult to compare different things with benchmarks, but there's, for instance, a yield benchmark. So with EIO, yield takes from 190 nanoseconds to 950 nanoseconds on this particular benchmark machine that we use. The Picos FIFO scheduler takes 130 to 330 nanoseconds, so it's quite a bit faster. There's also a semaphore, which is especially implemented in EIO, and we also have this semaphore implementation for Picos. And again, the Picos version is quite a bit faster. But of course, this is a bit like an apples and oranges comparison because the semaphore implementations are quite different. And the EIO implementation, it uses a very sophisticated data structure and algorithm, but it has not been optimized really carefully. There's also, I mentioned the tiny HTTP daemon. So there's a, it was benchmarked to be able to do like 500,000 requests per second on a rather beefy machine. On other machines, not necessarily performing that well. But the bottom line is that this should allow pretty efficient concurrency. And to end, so basically today, schedulers are deep, so they have their own implementation of everything. So it's going to be thousands of lines of code, and then all the extra libraries that you want. That's tens of thousands of lines. And with Picos, a scheduler can be like 100 to 500 lines of code. I mean, it's basically just a data structure and loop. Like I said, Picos trivializes the scheduler, so it's not unbounded complexity. It's just the multiplexer and timeouts. And then we can do all the other things as libraries, and they are fairly modular, simple things. Don't take a lot of code. So we get basically like all sorts of interesting combinations of things quite nicely. And in the future, maybe we actually don't want to talk about schedulers. We want to talk about concurrent programming models. So you want to use actors to structure your concurrent code. So maybe you have some sort of collection of things that work with a nice actor model, or maybe you want to use capabilities, then you have maybe a different collection. Maybe you want to use more traditional concurrency. There's maybe another collection of things that work with any Picos scheduler. And we could mostly share most of the other things, like the multiplexers, for instance. They are not probably the most interesting part to innovate on. So we can basically then combine these very freely. And this is probably much bigger change than what might be obvious, because this basically potentially eliminates the whole competition. So there's no need to compete or create like completely incompatible ecosystems. We could just work together. And here are some next steps. We're going to, of course, continue development of the Picos system. And yes, more is more. Thank you.
Thank you, Vesa. I'm sure you all have a lot of questions. We have time for a bit. Come here to ask them.
Given that EIO is also worked out at Tarides, I'm curious if there's been any efforts to move EIO to be based on Picos so that it would be interoperable with other things that way.
Yes, that has been planned to happen. So I believe Thomas will look into that in the future. So hopefully it will be ported to Picos.
One of the things that was not clear to me is the goal is to actually be the most efficient implementation to be used as a core, or to be like an actual standalone library that end application should use.
You mean the core library? Is it like? So the idea with the Picos interface library is that it provides you with this trio of concepts, and they are very low-level things which are designed to be to have like a very small memory footprint, but they're not designed to be necessarily like easy to use, for instance. So the idea is that you can implement then more interesting higher-level models efficiently on top of them. So that's the idea.
All right, I think that's it. Let's thank Vesa again.